Good afternoon and welcome to lesson number 19, where we shall continue to discuss sequence control. Today we will discuss a scan cycle, that is, a scan is a program execution. So, we will discuss how programs are cyclically executed, and we will discuss the nature of its impact on performance, and we will also discuss how to write some simple relay ladder logic programs. So, as usual, we view the instructional objectives first. After today's lesson, one should be able to describe a typical program scan cycle, that is, describe what takes place, how the program works cyclically, would be able to explain the impact of this kind of execution on the control performance, typically on the fastness of response, that is, how fast the programmable logic controller responds to changes in inputs with changes in output. Then we will go on to describe the basic elements of a typical relay ladder logic program. Today we will look at the very simple elements of the program, and in future lectures we shall go on to see more advanced programming elements. And finally, we will take two of the simplest examples and see how exactly a relay ladder logic program segment could look like, and also would learn to interpret a particular RLL program. That is, after if we are given an RLL program, then we have to know what it means and how the inputs and outputs will change with time. So, we will do that. So, that is the agenda today. Having said that, we continuing on the same note from the last lesson. If you recall, in the last lesson we had ended at a point when we had listed some of the hardware elements of a PLC system, namely backplane, CPU, memory, the different IO modules, wiring, programmer, man machine interface, etc. So, today we take a software focus and start looking at how the basic program execution goes in a PLC. So, this one, obviously in like in most control programs, a PLC program also works cyclically. So, as it happens, so basically these are actually so this is one view, say view A. In view A, we are indicating that the program simply works cyclically. So, this program, which is a set of statements, execute cyclically, that is, the execution begins here, then next statement and so on till the last statement, and then again the first statement will be executed. Now, what happens within this overall program box, that is, what are the functions which are carried out in the program. So, as we all know that PLCs are real time embedded systems, they are reactive in the sense that they accept inputs from the external world and produce outputs which go to the external world, namely the machines. So, obviously the program has to be always aware of what changes are taking place in the external world, namely the various variables that are being controlled in the machines. So, a typical program cycle includes 3 steps. First is, so this is an expanded view of A, namely B, which shows that typically 3 activities take place during a program execution. So, for the first one is read all inputs. Mark the stress on all, which means that it is not that. So, initially it means that initially all the inputs are read one after the other and their values are stored, and then the execution of the logic begins. So, this is a major difference with any standard program which you could write in a microprocessor. In a microprocessor you could write a program where the various processing statements, addition, subtraction, multiplication, comparison, whatever you have, you could intersperse them with the input and the output statements, but typically in PLC execution that does not take place. So, in PLC, because presumably because of the fact that initially the PLC programs, there is always a stress on keeping things simple so that errors do not occur. So, at the cost of some flexibility of programming, we are intending to achieve some simplicity, and that is a sound strategy provided performance is not affected. And in this case it happens that typical microprocessors statement execution times run in microseconds, while with PLCs the kind of things that we are trying to control are either mechanical or thermal or chemical. So, the time constants are usually so large that this subtle difference between reading all the inputs at one time makes hardly any effect. So, therefore, typically for PLCs all inputs are read at one shot in the beginning. At the beginning of the scan cycle, one cycle of these 3 steps would be called a scan cycle. After all inputs are read, the program logic gets executed. Now, during the execution of the program logic, various outputs are produced. So, it so happens that as outputs are produced, they are written to some temporary memory, but just like inputs are read at the same time, similarly it is not that whenever some outputs are produced and some output values are stored in memory, they would be going to the external world. That does not happen. So, after all the logic of the program is executed, at the end all the outputs are output values which go to the external world in the sense of various switches, motor starters, lamps, indications, they are all updated at the end of the cycle, and then the cycle repeats, namely the next cycle of inputs are read. So, this is the typical way that a PLC program scan takes place. And so, C is a kind of shows the kind of memories that are used in the PLC system. So, you have 4 kinds of memories. First, you have what is known as program memory, where the logic program is stored, that is the first one. Then you have what is known as an input image. So, when the inputs are read, they are for the program logic evaluation, these input values will have to be read from time to time during the evaluation of the logic. So, therefore, they have to be necessarily stored in memory. So, where the input values are stored is called an input image. So, this is the second use of the memory. Similarly, as outputs are produced, as the logic gets computed, outputs are produced and they have to be stored till the time that they can be transferred to the external world. So, for that the output image memory is used, and as we know that for all computation we need certain, in addition to the input and output variables, we need certain temporary variables which are so for storing these things we need some other additional memory. So, this shows how the overall memory available in a PLC system is used, right. Having understood that, we have to understand that this kind of a program execution we are in this figure, what we are trying to show is that many times it will happen that the if you let's first look at the, if you have to understand this diagram, before that we have to understand a typical PLC hardware organization. So what happens is that in a PLC the various units, this we did not discuss in the earlier lesson. So the various units are actually organized as modules. So you have what is known as racks. So this is one module. Similarly, there could be another module by the side of it. So this is one module, this is another module. Similarly, so this could be the main processor module. Similarly, this could be an analog IO module, input module, let us say. Similarly, you can have digital input, digital out, various kinds of modules. So what happens often is that, so now you see this processor, the external variables, that is the various signals, get interfaced to these modules, and similarly this could be a digital output module. So what happens is that these external signals are, these modules are again self independent, they are as such independent circuit boards. So they often have processors on them. So what happens is that the processor here, actually what happens is that here is a board, suppose we are taking, so you have all the circuitry here. In this side the physical signals are interfaced, physical or field signals, and on this side so these are physical signals, and on this side symbolically maybe in a buffer, this is a buffer, the values of these signals are stored. So when the processor module reads an input, it is not that it reads these physical signals, it actually reads these buffer values which are stored, which are continuously kept in the buffers by the IO cards, right. So and these IO cards often work under the control of the processor. It may work at the control of the processor, or it may continuously, or it may work independently cyclically itself, right. So all these IO cards are actually there is what is known as, that is what we referred to in our earlier lecture as a back plane or a bus, back plane or bus, which is nothing but a set of conductors to which all of these are connected. So when I say that a processor reads an input, it actually reads these buffer values over the bus. So actually two activities keep on taking place. The first one is that the physical signals keep getting transformed from either to these buffers, and these buffers could be physically situated either on the card, or it could even be situated in the processor memory. So it may so happen, those who have studied microprocessors will understand this, that it may so happen that these cards every few units of time convert these values, and then using some interrupt mechanism they will transfer these values to some part of the processor memory. So what I am trying to stress is that here there are two kinds of cycles going on. One kind of cycle continuously cyclically samples the physical inputs and transforms them to a part of the memory which we call the IO image, and the processor when it reads, it actually reads from that image, right. Now, so having understood this, so what is happening is that, so you see these are the various racks, these are the various racks. So, these are the IO racks, this could be an analog in, this could be an analog input, similarly this could be a digital output, various kinds of things. So, there is a scanning mechanism which goes on, which continuously updates, either reads from the racks depending if it is an input rack or writes to a rack from a part of the memory. This memory can be at the scanner, can be at the cards, at the various places. Okay. While the main PLC program scanning actually reads these IO images, from this IO image it actually reads the inputs, and whenever it actually produces outputs, it also writes to this IO image, and so it keeps writing to this IO image, and then finally they get transferred to the racks. So, this is how the basic activities go on in a PLC. So, now we have to see that what is the result of these activities, this kind of scanning, what kind of response, what kind of impact it has on the various input and output updating. Typically, we are interested to know how much of delay we can expect in responding to an input change. So, imagine that this is there could be a best case and there could be a worst case. So, we are first looking at the best case. So, what could happen is that remember that the planned input can change at any arbitrary period of time, we cannot control that, right. So, suppose the planned input changes just before the inputs are read. So, then immediately after it changes, it will be read, that is, this change will be reflected and will come to the processor IO image very quickly. Then while the program will be executed, then in computing the output value, the latest change of the input value will be taken care of, will be accounted for. So, possibly due to this input change, at the end of the execution there will be an output change. Now, since it may actually happen, suppose this is the ith statement. This is the ith statement, that is, the effect of this input is used to compute some output at the ith logical statement. So, then what will happen is that during execution, here is this is the point where the ith statement gets executed. So, actually in the processor memory, the output changes at this point of time. However, it does not go to the physical world till the whole program execution has completed, as we have said. So, therefore, the output, the physical output which goes to the process gets affected only at that time, and there is this is the amount of delay that is bound to occur. So, there is the best case response time is the delay of one scan, which depends on many factors like the speed of the PLC execution, also the length of the RLL program, etc. This is the best case. It is called the best case because the input was read immediately after it changed. So, there was no delay in sensing the change in the input. In the next case, as we shall show, that we shall see the worst case where this is just the opposite. Oh. So, this is the opposite, this is the worst case. So, what is happening here? Here unfortunately the input has changed just after a reading cycle was completed. So, therefore, this change of the input was not sensed by the PLC in this scan cycle. In this scan cycle it did not sense that the input has changed. So, therefore, it computed, by this time it had computed and sent out the outputs once, but however those outputs did not reflect the new value of input which occurred just after the input in this cycle took place. So, that is why it is the worst case. So, it occurred. So, there is a maximum possible delay. However, at this point in the second scan cycle the inputs will be read again, and this time this change is going to be sensed, and now after this, after having sensed this, there will again be one cycle of delay. So, therefore, the worst case of delay is 2 scan cycles. So, that is why depending on the kind of response time, one has to decide based on an application whether such delay times are acceptable or not. So, we shall see that in certain cases these such delay times may not be acceptable, in which case you have to take additional measure, in the sense that you might put additional cards or additional hardware for taking care of them. So, this is a case where you get very fast pulses and one has to count those pulses. So, in this case what we see is that, suppose the one scan time is this much. If we have to count the number of pulses which are arriving on a pulse train, typically such pulses come from shaft angle encoders. If we have to count them using the PLC itself, then if we can see that if the pulse trains are slow enough, that is the pulse width are sufficient, then for this width of the pulse train all the level changes will be sensed. So, we are essentially going to count the number of pulses by counting the number of level transitions. So, then our count is going to be correct, and if we compute the speed based on that, the value of speed we get is going to be correct, and so will be our control. On the other hand, if we increase the speed, in which case the pulses will be of shorter duration and they will arrive faster. So, we will see that most of them are still being sensed, while suddenly one pulse is missed. So, you see that the program was scanned for this pulse, when the program scanned it, the value was 0, and when the program scanned it next, the value was again 0, and so the program assumed that it remained 0. So, one that it went up to 1 in between and came down is not will be, I mean the program will be unaware of that, and therefore there will be perhaps a small delay in the computation of the speed. If you have faster pulses coming out, still faster, then many such pulses will be missed. For example, this one, this one, this one. So, it will be more of a chance to see when, for example, this pulse will be counted, this pulse will be counted. So, you will get, you will get drastic. For example, in this pulse actually what will be inferred, when it was sensed here it was 1, when it is sensed here it is also 1. So, therefore, it will be assumed that it continued at 1. So, the inferred pulse is going to be, in this case the pulse count will be severely wrong. So, it will assume that it has continued here and then it is continuing here and then it is continuing here and then it is continuing at this point it is rises. So, the count will be a small fraction of the real speed and we are going to be totally out. It is actually for this reason that for counting fast pulses you cannot use the PLC itself, but rather use a special card. So, that card does not have the purpose of that card is solely to count the pulses coming from such a fast shaft angle encoder. It is not loaded with any other task. So, therefore, it can really sample that line very fast and therefore, can compute the speed, and the speed can be made available to the PLC in terms of a value. So, rather than the PLC counting the pulses, somebody else will count the pulse and will convert it to a value which the PLC will read from time to time. So, it is for such reasons that sometimes special functional modules like as we mentioned in the earlier class, that sometimes special high speed counter cards are needed. It is for this purpose.